Thank you very much, and thank you for inviting me to be here. This morning I'm going to talk about, it's not close enough. I'm going to talk about, like the title suggests, closed theories. This is an idea that was popularized by Werner Heisenberg, but let me just try to motivate this talk by talking about Kuhn. I have two remarks to say about Kuhn just as an opening ploy. So Kuhn's Structure of Scientific Revolutions appears in 1962, creates a lot of interest among philosophers, historians, and sociologists even, and even other disciplines in social science. However, it's remained largely incomprehensible to physicists and mathematicians, probably other scientists too. Just the idea of scientific revolution was problematic. The idea of incommensurability, also promoted by Kuhn, is just not understandable to them. So I would say if you did a survey, this is for our sociologist friends, did a survey on exact scientists, you wouldn't find a lot of people who were on board with the idea of scientific revolution. For contemporary philosophers of science, however, they're very much impressed with Thomas Kuhn, not all of them, of course, but the rationality of science for a lot of them hinges on the construction of abstract models of natural phenomena. Right, so this is what I'm focusing on here. And with the idea that since the advent of relativity theory, 1905, model building implies, to a greater or lesser extent, an appeal to these things called closed theories. So what I'm focusing on here is essentially a working philosophy of scientists. So I mentioned Heisenberg. Here he is. Here's the young Werner Heisenberg. We know him as an early post-relativity physicist, born in 1901, student of the famous relativist Arnold Sommerfeld, co-founder, of course, of quantum mechanics in 1925, and a major professional influence on 20th century physics, not only from a conceptual and cognitive and physical standpoint, but also through his professional mentoring of doctoral students and postdoctoral students. There's an interesting illustration of this in this physics tree. If you Google physics tree, you see it presents in a very interesting way all the students and mentoring relationships that Heisenberg had. And it was just to show, for those of you who aren't physicists, the importance of Heisenberg in this story. So what are Heisenberg's closed theories? This is something he proposed almost immediately after discovering quantum mechanics in 1926, essentially. And he can continue to develop and promote this theory until the end of his life on separate occasions, always in non-scientific contests or presentations of more of a philosophical nature. So there are essentially four features for closed theories, which Heisenberg proposed. This is a version that comes from a publication in 1948. They're characterized by consistent concepts articulated via axioms. They are empirically adequate representation of natural phenomena within certain application domains. They don't purport to be theory of everything. There are exact boundaries of these application domains that we don't know. So the idea is science is actually working on determining the boundaries of these application domains. And these closed theories are the basis for further research, not only in determining the boundaries of application domains, but also in developing current theories that will take into account other phenomena and other theories which could themselves become closed theories. He provided an exhaustive list in 1948 of four closed theories, including Newtonian mechanics, a kind of a poly-theoretical view of electrodynamics, optics, and special relativity. So these are all kind of folded into one. There's of course, a reason for that. And then a third closed theory was the combination, also polytheory, of classical thermodynamics and statistical mechanics. And then last but not least, of course, quantum mechanics. So we have four closed theories, along with two negative examples, which is to say, two recognizable important theories in 20th century physics, which are not closed, including general relativity and nuclear physics.
What's the other one?
Nuclear physics? Heisenberg did not rule out the possibility that these two negative examples could become positive ones someday. This is a possibility, but he couldn't affirm that. So this is the idea of closed theory is what I call CTM, the closed theory model of science, as opposed to Kuhn's model of science, has interested professional philosophers of science, including Catherine Chevalier in her introduction to Bohr, some Bohr's philosophical writings. This approach of closed theories generates as many problems as it solves. So there's this typical frustration of a philosopher of science with Heisenberg's presentation of this theory as not being that of a professional philosopher, essentially. So it's difficult to know for sure what Heisenberg meant. Mara Beller, in her 1999 book on principle of correspondence and history of philosophy of quantum mechanics, she argued that classical physics was not a closed theory, given the rise of chaos theory. I think this is just a fundamental misunderstanding of closed theories. I think she's just not understood what it's about. So I would contest that criticism of Mara Beller. Also, the pluralist philosophers of science, Scheibe and Bokulich, both see CTM as a pluralist theory. And I think I agree with them, actually, for what it's worth. This is a pluralist approach to science. And then the last person here I'll mention is Gregor Schiemann. In a 2009 chapter, found also CTM to be entirely plausible, and he drew an affinity with hacking styles of scientific reasoning, which David mentioned yesterday, which is then purported to be a foundation of scientific objectivity. So this is the way that philosophers have come to grasp and understand this closed theory model. The question that hasn't been asked, but I will ask now, is CTM a form of conventionalism? Poincaré and Heisenberg both preferred a neo-Kantian framework. Hilbert promoted the idea of axiomatically closed or self-contained theories, so not conventionalist. Normally, we oppose Hilbert and Poincaré on many issues, and indeed they have clear opposition in their lifetimes. Physicists, however, including Max Born, found Hilbert's axiomatic approach to physics to be simply unadapted to their domain. Heisenberg's sources in coming up with this idea of closed theories were many and varied, and I don't pretend to know exactly what's going on here. Notably, we know that Heisenberg attended Hilbert's lectures in Göttingen in 1922. We also know in 1922 that he studied with Born Poincaré's méthode nouvelle de la mécanique céleste, and this is hugely important because he was trying to come up with an understanding of quantum phenomena, and he actually did. All right, so I'm not going to solve this, but evidently I'm not kind of pursue this relationship between closed theories and conventionalism. In both conventionalist philosophy of science and closed theory approach, we have conventions and closed theories that are true come what may. That is, they are immune to empirical refutation. This can be somewhat shocking for a physicist, but that's the way it is. These abgeschlossene Theorien, they're unimprovable, closed to future changes. That's what makes them closed theories. They're closed to future changes. It's not that they're closed axiomatically. They're closed to future changes. All right, and they're also essential to the progress of science. This is clearly what Poincaré said about conventions. Both Heisenberg and Poincaré recognized explicitly the discursive foundation of science. So there's a linguistic role here. Poincaré argued at the end of his life, in fact, at the very last year of his life, for a conventional view of space-time, while, of course, Heisenberg identified special relativity as a closed theory. So there's this overlap as well. However, I think there are differences between closed theory and conventionalism. Notably, Poincaré considered certain principles to be true for all time, not necessarily theories. So that's not the way he presented conventionalism. Heisenberg then obviously considered certain theories to be true for all time and didn't break that down into component principles, for example. And then afterwards, Poincaré's philosophy of conventionalism, also Heisenberg's closed theories, were taken up by the Vienna Circle, and so that gave it a life of its own among philosophers of science. So here I get into what I really wanted to talk about was what happens to this CTM closed theory model in 20th century physics. To what extent, to what degree does CTM reflect the working philosophy of science? We find explicit reference to abgeschlossene Theorien here and there, but it's not you don't find it everywhere. More generally, what you find are appeals to one or more of Heisenberg's four closed theories that appear in the work of leading theorists. And here I'm going to give you the examples of Einstein, Niels Bohr, and last but not least, George D. Birkhoff. I said in my abstract I was going to talk about von Neumann also, but I saw that we're going to have talk about von Neumann later, so I would skip that. That gives us more time. So Einstein. For Einstein, at least at the end of his life, he said that there's only one theory that's closed. Already when he presented special relativity in 1905, he posited that the laws of classical mechanics hold good in one frame of reference. So he essentially had to admit that classical mechanics was valid in some sense in order to identify a single inertial frame of reference. This is, of course, not a philosophical presentation, it's a scientific presentation, but it's the foundation of special relativity. Later in his life, which is to say in his autobiographical notes published in Schilp's volume, he wrote that classical thermodynamics was the only, this is a quote, only physical theory of universal content for which I am convinced that in the framework of the applicability of its basic concepts, it will never be overthrown. If that's not a closed theory, I don't know what it is. So of course, there's no reference to Heisenberg, and he maybe have come up with this on his own. And certainly he didn't draw any connection there. Niels Bohr, here he is. Bohr's correspondence principle has clear relevance to closed theory. He came up with his correspondence principle well before then, and that's also Planck's correspondence principle of 1906. So this is already in the air when Heisenberg was 5 years old. So, and also there's obviously a close relationship between Heisenberg and Bohr. They didn't quite agree on the meaning of correspondence principle, but as Marabella has demonstrated to everyone's satisfaction, there are 100 different interpretations of correspondence principle among the actors of quantum mechanics. And Heisenberg naturally deferred to Bohr on this point. Nevertheless, Heisenberg also emphasized the correspondence principle's importance to the discovery of quantum theory. So, for non-physicists, correspondence principle is well, grossly stated in one version. Well, let's take the Planck version, it's easier. It's the idea that you can recover classical behavior in the limit of h going to 0, right? So it's a nice asymptotic relation. So you have if you start from quantum theory, in quantum theory, then you'd have quantum numbers, and for high quantum numbers, and then you'd recover classical physics. That's the idea. So you have classical physics as a closed theory, and then you have quantum mechanics, and the relationship between them is this correspondence principle. George Brooke, how are we doing on time here? Great. So George Birkhoff was probably the first American mathematician to achieve general recognition among Europeans. So he's an American product. He became a professor of mathematics at Harvard, but mostly he's known for the fact that he found a proof of Poincaré's theory, geometric theory, in 1912, a theory that Poincaré himself said he could no longer work on. He was too tired, and then he died. And Birkhoff actually was able to solve this, and so that was actually a demonstration that he was at least in a class with Poincaré, which is pretty good. That's a nice class to be in. So Poincaré is working in this field of systems dynamics, and he's clearly become a mover and shaker in that field. And so he extends Poincaré's methods, particularly using not only topological methods, but measure theory, which didn't exist in Poincaré's time, or barely, it was just being invented. And so that was published in his book, Dynamical Systems, in 1927, which would then be central to systems dynamics research. But he's also, of course, well known for his demonstration of what's now called the Birkhoff theorem in general relativity, which concerns the static nature of a spherically symmetric metric in vacuum. And now there are several versions of Birkhoff's theorems for more complicated situations in general relativity. But this is a fundamental contribution to general relativity theory. And so Birkhoff is clearly interested in general relativity and actually publishes also popular presentations of general relativity. But it's clear if you read these books that what he's really impressed with is special relativity. He's not fully convinced with this whole curved space-time thing. So what happens in 1931? Of course, this huge discovery of the proof of the strong proof, the ergodic theorem, and then the next thing we know, this is actually the three areas that were retained for his biography, obituary written by Veblen, were work on ordinated differential equations, dynamic theory, and the third thing was this theory of gravitation. So this theory of gravitation is what I want to talk about now. This is what he first published in 1942. It's a Lorentz invariant theory of gravitation. And the first time he unveiled it was in Mexico. In Mexico City, there was a meeting of physicists. I'm not sure exactly where now, but so there's an interesting Mexican connection, which I'm glad to present. So this is a flat space-time tensor theory of gravitation. It was purported to capture all three classical tests of general relativity, which is pretty amazing. Right? You think general relativity with its three classical tests of advance of the Mercury's perihelion, things that Newtonian gravitation cannot do, bending of a light in the vicinity of a large mass like the sun, and the third is redshift in the vicinity of a massive object. Birkhoff's flat space-time theory of gravitation captured all of these. It wasn't simply an equivalent representation, but the representations of these phenomena were close enough that they were you couldn't distinguish the general relativistic prediction from Birkhoff's prediction. The collaborations here that I mentioned include, including co-authorship, took place with the UNAM colleagues Alberto Barras, who Carlos knew personally, I'm glad to say, he told me. He can vouch for that. Carlos Greff Fernandez, founder of the physics department here, as I understand. Manuel Sanuel Bayata. Please correct my pronunciation. And Marcos Moshinsky, who is a Kiev-born physicist who was trained in, actually took his PhD thesis under Wigner in Princeton, and then came and became a professor of physics at UNAM. And another person who I don't know much about yet, Fernando Alba, but who I understand he was also a president of the Mexican Physical Society and directed the Revista Mexicana de Physique. So these are some of the collaborators who pursued then this flat space-time theory of gravitation. And well, it was pretty much up to them because notice the death date of George Birkhoff. He died in November 1944. So he didn't have much time to really develop these collaborations, but he spent time in Mexico City. There's a correspondence in the Library of Congress about these visits and his collaborations. And he also arranged for visits and invitations by Gray Fernandez at the Institute for Advanced Study. Gray Fernandez then derived, I think in 1944, a two-body solution, which is available also for general relativity, but extremely hard to come up with. That was in 1934 that Einstein was able to derive from the full field equations a two-body equation. So Gray Fernandez came up with that right away. It was one of the first results from the Birkhoff theory, and so that was also, you know, showed the simplicity of doing a two-body solution in this theoretical domain. So that was also an advantage to Birkhoff's theory. Yes, I mentioned the invitations to Institute for Advanced Study. There was actually a meeting between Gray Fernandez and Einstein. Apparently, I don't know exactly how that came about, but there's a publication where Gray Fernandez recounts his meeting with Einstein, and Einstein was not happy. Einstein essentially tried to convince Gray Fernandez that, no, you're on the wrong track here. It's my theory that's the right theory. And but Graf Fernandez was not perturbed. He said, he was we say in French, droit dans ses bottes. But the arguments that Einstein essentially was trying to say is, this is unphysical and what have you. And of course, Einstein wasn't the only person to have criticism of the Birkhoff's theory. Hermann Weyl, interestingly enough, immediately engaged with this. And also Howard Percy Robertson, which by that time was probably the premier American physicist working on general relativity. He was at Caltech and taught general relativity. Meanwhile, I believe Birkhoff was teaching relativity at Harvard, but more in a along his style, and surely presented his theory as well, based on more of a linear theory of gravitation. In fact, this is what how Weyl and Robertson criticized Birkhoff's theory, is that in general linear theories are inadequate. But okay, all right, but you have to recognize that. How did Einstein first derive the advance of the Mercury's perihelion? He used the linearization, because doing anything with the full nonlinear field equations of relativity is just extremely hard. We can do it today because we have help from computers and advanced mathematics in dealing with nonlinear field equations. But at that time, you pretty much, in order to get any kind of prediction related to observational effects, you had to linearize. And so this, I think there's some feeling by the part of the general relativity community that this is just too easy to do the linear theory, right? And that's essentially the template for Birkhoff's theory, right? Because he takes a flat space-time and then you add to that your matter fields. It's a dynamical field, which also was somewhat speculative, because he came up with this thing as a perfect fluid, which was then supposed to communicate dynamic effects at the speed of light. So these are empirical. This is how he came up with empirical provisions from this theory of Birkhoff's. From an empirical standpoint, Birkhoff theory was judged to be non-viable by Clifford Will, who's well known for his comparison of alternative theories to gravitation and general relativity himself. Why did he say it was non-viable? He didn't really go into the details, but he said it was the non-viability of Birkhoff theory was due to a constraint on pressure that had to be equal to the matter density times the velocity of light squared. This is a mathematical constraint on Birkhoff's theory. And so you say, well, what's wrong with that? Well, that means that you can't make sense of, essentially the velocity of sound, for example, is going to be equal to the velocity of light, which is contrary to what we know about the velocity of sound, right? So I don't know, maybe it's not, I'm not sure that this is as serious a problem as Will says it is, because all the scholars who were working on Birkhoff's theory understood this to be a work in progress, and they knew they didn't have the answer to everything, and also they felt that this is promising. I mean, if you try to understand what was the interest of working on Birkhoff's theory in 1942 in the 40s, it was because it was a potential unified field theory, and Birkhoff and his Mexican colleagues presented this way, saying this is we're going to be able to actually integrate quantum theory and electromagnetism, and so this will be a unified field theory, which is exactly what Einstein was pursuing as well, right? So you can start to understand how this would be of interest for theorists. So what happened to Birkhoff's theory? Well, there are a number of more than a dozen publications that come from this Mexican group around Graf Fernandez and Vallata. That it kind of peters out in the late 50s, I would say. I think the last there's a paper by Graf Fernandez in 61, and then there's another paper in 63 by somebody who's not in that group. But I think what happens is that this flat space dynamical approach to gravitation was revived, but in a more of a Einsteinian context, or maybe I should say Hilbertian. right? So I think what troubled Einstein with this Birkhoff theory was that it was just physically there were difficulties with it, and obviously it couldn't deal with strong fields. I mean, this is the problem with all linearized theory of gravitation is you don't get all the wonderful nonlinear effects from strong gravitational fields. Feynman comes in. Okay, in 1961, what happens in Caltech? Robertson retires, and he's replaced by Richard Feynman. Richard Feynman comes in, and now he's in charge of teaching general relativity. And how does he teach general relativity? He doesn't teach the geometrical approach. He teaches this field theoretic approach, which, and he's got the most brilliant young physicists in the United States, and not just the United States. And so he trains an entire generation of young physicists using this Hamiltonian field theoretic approach to general relativity, which, as we know, is mathematically equivalent to general relativity, right? But so why did Feynman make this choice? I don't know. I'd like to know more about this. I got to talk with the Feynman specialist. So it's inspired, of course, by the variational derivation of the action integral that Hilbert found in 1915, formally equivalent to general relativity. Gravitation, in this case, arises, like other forces, via the exchange of dynamical fields propagating through Minkowski spacetime, right? So there's no appeal to curved space, which when we think of general relativity, if we learn general relativity, this is all about curved spacetime. It's, so matter is coupled to geometry. It's very exciting. But for Feynman, no, the theory of interest now is quantum field theory. And this is about field physics. So in both Feynman's approach and in Birkhoff's approach, the metric tensor is a conventional combination of the Kronecker delta and the fundamental gravitational field, h mu nu. So I underline the conventional here. The convention is that you're starting from flat spacetime. Flat spacetime is the closed theory that you're using now to understand general relativity, or understand nature if you prefer. But the closed theory is actually in there. It's built in. And you say that's conventional. So then there are problems. What the course was the problem for Einstein is that you still have to interpret these equations. And if you don't have curved spacetime as a source for interpretation, you run into trouble, right? And so this geometric approach of the original Einsteinian approach with curved spacetime remained dominant in physics. It still is dominant today, thanks in part to some astronomical discoveries, distribution of radio sources that Martin Ryle compiled in Cambridge in the 1950s, which then killed steady state theory in cosmology. The discovery of cosmic microwave background radiation by Penzias and Wilson in 1964, giving a further boost to cosmology. Cosmology becomes more important, and that becomes really difficult to do with this field theoretic approach. And I think what's important here also is the Penrose singularity theorem in 1965, which you don't get, you get from the full field equations, and then that gives us a good reason to believe in black holes, right? Which are also very strong gravitational fields, which you're not going to get from a linearized theory of gravitation. So here's a little scientometrics for you. This is how are we doing? I can't read that. Okay. You need to draw it longer and darker. I'll be done. So this is a graph of, you can't really see the bottom here. Oh, well. There, you can see the bottom now. So it goes from 1915, so the discovery of general relativity, to 1975. This is essentially world of science references that have the word gravitation in them, or relativity. It's a number of keywords that we use to pick out this set of publications. The date here is 1915. This is number of publications. Number of publications against time. And so, yeah, so see what's happening here, 1950, 51, and it takes off. So this is a question for historians. Why does it take off in 51? And so this is actually compiled by Robertson and his friends at Max Planck, using all the resources of the Max Planck Institute for Wissenschaftsgeschichte. So I'm putting this here because you can see it's kind of remaining rather modest, and then something happens here. And part of this something happens, well, 1961 is right here. That's also, I think, new methods, field theoretic methods coming online, and you've got all these young people trained in it. Kip Thorne, I was a student then, I was using all these methods. And so it really takes off. And so, yeah, in the 60s, there are a number of things that are happening. I mentioned these, so that affect not only the utility of field theoretic methods, but also interest in cosmology and general relativity in general. So this is a historical question for us. So this is my last slide. There are a few open questions with respect to closed theories. Actually, many of them. From a philosophy of science standpoint, the question is CT-ness, that is the quality of being a closed theory, to be decided empirically or formally? Heisenberg didn't say. We don't know. Could be one, could be the other. Is general relativity now a closed theory? You can take a vote here. Yeah. But Weizsäcker, who was Heisenberg's star student, thought at least in 1987, that general relativity had become a closed theory. Are there other closed theories? How does this worldview, the closed theory model, play into what ways that scholars can trace? Difficult. And here I just give a shout out to this publication by Roberto Lally, Dirk Wennergren, and another fellow in Einstein studies, where they present a scientometric and a social network theory analysis of these networks and clusters of scholars and scientists working on relativity theory and publications. And so give us a nice quantified view of importance of particular publications, measuring centrality for particular publications, and then that we can judge whether that matches with our understanding of how general relativity actually became the phenomenon that it is today. So that's it. Thank you.